my call because I had to go. So there are, I think, two parts. So one part has been already taken care of by some other professor, and my part will be actually DC and induction motor drive system. Okay, so the other part is by the calculations regarding say 4-quadrant operation, and then thermal rating calculation. All those things are there. So those classes that will be taken by some other professor. So in this class, we will be covering mainly 2-3 drive systems. One is induction motor, another is DC motor, and then synchronous motor. Okay. So I think looking at the importance of the industrial system, what we have. So I am starting with induction motor, then we will go for the DC or synchronous. Okay. Because you see that in industries, wherever you go, so you will find that 80 to 85% of the motors are induction motors, 85% motors. So therefore, I mean, it is better to study it in a more detailed fashion rather than those other machines whose drive system although exists, but actually, hello, it is not there. If it is not there, I'll be trying to do something.
No, sir, no, sir.
It is there.
Yes, sir, yes, sir. All fine, sir.
Screen is visible, na? Screen?
Yes, sir.
Okay. So okay, so that is why I am starting with induction motor. Okay, so now you see induction motor. There are specific, the operation of induction machine. So any one of you, if you just tell me how an induction machine operates. I mean, whenever the voltage is given to the stator, three-phase balanced voltage. So what happens to the machine that it rotates? So do you have any? I think you have idea, but can you explain this?
So it creates rotating flux that induce voltage in the rotor part, and rotor that induced voltage will create another rotating flux, and those fluxes, I mean, the reaction between those fluxes will create the rotation.
Now the first question was the rotating flux is produced, rotating magnetic field or rotating flux, because you are giving a pulsating three-phase flux. Okay. So why rotating flux is produced? So that should be clarified. So how?
So the rotating flux is created because
we apply time displaced current to phase displaced winding. So by in that
phase displaced means actually space phase.
Space displaced,
okay.
Yes, sir. Space displaced.
These windings are placed 120-degree electrical apart in space. Okay, so if you combine these two, right, space displacement and time displacement of the three phases, so you get a single field which will be rotating in nature. Now, if it is not, it is the open type. Okay, if it is an open type, suppose you cut open the rotor and make it flat, so it will be actually a traveling magnetic field. Okay, so this is, so it is confined within space 120 electrical degrees, so that is why you get a rotating field. That's all, fine. So now actually starting from there, if you see that the machine tries to rotate, the rotor tries to rotate in the direction of the magnetic field, and actually it will try to catch the magnetic field because of Lenge's law or something to remove the effect of production of flux in the rotor. So actually now what happens? So then what I find, or what I find actually from here, that the speed of the rotor is mainly governed by the speed of the magnetic field, speed of the rotating magnetic field. Okay, so now then the majority, or you can say all the speed control of induction will confine within how to vary the speed of the rotating magnetic field, right? So now you know the rotating magnetic field speed in RPM. I think you have calculated from your BTech second year classes. That is 120 F by P, right? The speed of the rotating magnetic field in RPM, it is 120 to the supply frequency divided by the number of poles in the winding, right? So then naturally the speed control technique will be actually to vary the rotating magnetic field speed, and one of the parameters are pole. So 120 F by P, so that means P is the pole. So the first method came that if we can change the poles, right, online, that means while the motor is rotating, so then naturally the motor speed will automatically vary. And the second method is actually the variable voltage constant frequency. I mean, you can vary the voltage, that we will see later on, okay, how it happens. And the third method is variable frequency. Normally, variable frequency, you know that 120 F by P. So naturally, it is also proportional to the frequency of the supply voltage. And again, the other technique, like all these three techniques have got some advantages and disadvantages. And to remove those disadvantages, the other modernized techniques has been employed, like constant volt by Hertz control, I'll say, out of which open loop and closed loop, and then constant air gap flux control, field orientation control, and the other one is direct torque control. So I have skipped it, direct torque control, because it is mainly for the PG syllabus. So therefore, we'll go up to field orientation control. Okay. So now these are the methods, right? So now if you go for the analysis of the how it is done practically. So just 1 minute. Am I in the slide or the other one? Right. So, right. So then we for the analysis of the drive system, so we go for the equivalent circuit model, right? So the screen is visible, na? Equivalent circuits.
Yes, sir.
Equivalent circuit.
Yes,
Okay.
sir.
So now you see that in the induction machine, equivalent circuit, when it normalized from the stator side, so we get RR as RR by S, and this is XLR actually, as I have said, XR actually is rotor leakage reactance, okay, and this one is stator leakage reactance, XLS. This stator resistance, this is rotor resistance divided by slip, and this is actually the magnetizing reactance, XM, and it is Flux resistance. Okay, so this is gives you the equivalent circuit of the machine. So now if you analyze it, so again this thing same I was talking about, that the motor speed is given by the rotor speed is given by the speed into 1 minus s, ns into 1 minus s. So normally we try to vary ns to vary the motor speed, because the factor of slip is very negligible. But actually this when you go for crude control, that means you don't bother about, say, difference between reference and the actual values by, say, 1%, 2%, 3%, or 4%. So you should not bother about the slip, but actually slip represents the load. Slip represents the load. Now, therefore, actually to have precise control, so you should account for the slip also. So at present, we will go for the crude method, like we will try to vary the synchronous speed, which is given by 120 F by P. So now you come here. So now if you look at the equivalent circuit, and the reactance XM2, XM, reactance XM, that means in this circuit we showed that this XM is a magnetizing reactance. If you compare the magnitudes or the values of XM and RM, you will find that XM is at least 3 times lower, at the rated value, at the rated condition, compared to the core loss resistance R, right? So at least 3 times. It can be 4 times also. I mean, depending on the line of machine. So therefore, in this equivalent circuit, to simplify the model, so we can neglect RM, because the current through RM will be actually much lower compared to the current through XM, right? And secondly, also that if you see that xm square is much larger compared to rs plus jxls square, right? That means magnitude of this magnetizing reactance is much larger compared to the stator leakage impedance, known as stator leakage impedance, right? So if I give you the value for a standard, say 1 kilowatt machine, that value of RM happens to be around say 4000, right? 4000 ohm at rated condition, 415 volt, say 1 kilowatt, 1440 RPM machine, and value of XM is around say 250 to 300 ohm. Okay, so therefore you see the difference is very large, and at the same time value of XM I have said 250 to 300, and value of stator impedance will be about say 10 to 12 ohm. So it is absolutely negligible. So now when you look at this equivalent circuit where this portion is very large, so current through this is almost negligible compared to this, so I can open this, and secondly I have this impedance which is much lower compared to this. So there is so when the impedance is low, normally voltage drop across this impedance also will be low. Okay, voltage drop across this impedance. So naturally, the current flowing through XM will be almost same when we place it here or I place it supply end here, right? So therefore, we can easily modify the equivalent circuit like this. So this is XM RM, and then this has been shifted to the stator side like this without this RM. So why we are doing this? Only to have a simpler calculation to obtain the torque, because if you place it here, so only you have the stator voltage and stator current parameters known and the equivalent circuit parameters known. So then the torque is actually IR square RR by S, 3 by omega S into IR square RR by S. So to find IR, what you have to do, you have to divide voltage by this total impedance, right? And the total impedance will consist of two parallel paths and a series combination. So this is this, and will be in parallel and then in series with this. So ultimately it's a, again if you get the stator current, to find the rotor current you have to apply current divider rules and all, and then find the rotor current. So it becomes a little bit tedious. Okay, you can do it, and the calculation will be very much you can say accurate also. But here with a little drop of accuracy, we get fairly accurate value of the calculated torque with a very simple calculation. Like when you shift it here, so I can divide stator voltage by this impedance to find the rotor current. So that is why I think you have done it in your BTech second year classes also, right? So therefore, actually, we get the simplified equivalent circuit. So this was air gap, this has become air gap, this is rotor, this is stator. So now from this you can calculate rotor current by this equation. So Vs by this one impedance. So actually RS plus RR by RR dash by S. So RS plus RR dash by S plus J XLS plus XLR, right? So in magnitude wise, you can have it like square root under RS plus RR dash by S square plus XS plus XLR square under root. So you get the rotor current. So once you have got the rotor current, you can easily calculate the torque. So why I am doing all these things? So I'll be explaining slowly. So we can get the expression torque. So torque, I was telling that 3 by omega S into R square. So IR square, again this is BS square by, so square root is gone, square RS plus RR dash by S square plus XLS plus XLR square into RR dash by S. So just I have actually rearranged the equation to look in a different manner. So this is 3 IR square RR dash by S. So up till this, I think, have you any problem? So am I clear to you? Because my audibility and all is clear to you.
Yes, sir.
Yes, sir.
Okay. Okay. So now we have got the expression for torque. Okay. So now we will see that why the need of speed control is there. Okay. So now we see that if you try from this expression, if you try to plot torque versus slip characteristics in the positive slip region. Okay. Positive slip means actually between 1 to 0. So positive can be also 2, but when you go back to the region of say increasing slip beyond 1, so slip 1 corresponds to actually stationary rotor condition, because you see the definition of slip is omega s minus omega r by omega s, right? It's a by definition it is the per unit, so difference of rotor speed from the synchronous speed in per unit value. Okay, so now when the difference is same, that means omega r is 0, so you get slip is 1. So slip greater than 1 is actually it goes to a situation where actually it's in braking region. So omega r is negative actually. Omega r has to be negative, right? Omega s minus omega r. So omega r, if it is positive, so then always this value will be less than 1 slip value, right? Now slip value greater than 1 means omega r is negative. That means your field in one direction and in other direction. So this happens only in the region of braking. So that you will be learning later on. But anyway, if you plot between this s equal to 1 to s equal to, I have lost there, okay, s equal to 1 to s equal to 0, so you get this black characteristics, like this machine characteristics, like this is the machine characteristics, torque speed characteristics, and this becomes your starting torque, this is the maximum torque, and this is the stall torque. That means sorry, this is this is the starting torque is the maximum torque, and this is the actually that torque zero condition. See,
sir, your cursor is not visible.
Cursor is not visible.
No, sir.
Oh, so how to do it? Anyway, so it is indicated. It is indicated here. See, torque T max. T max is indicated here. This is a maximum torque. Its other name is pull out torque or stall torque. Okay, and this is starting torque. So at the beginning, you see at s equal to 1. When motor speed is 0, I mean the black line starts from TST. This is a starting torque. Okay, is it visible?
Yes, sir.
Now at slip equal to 0, that is at synchronous speed, you get 0 torque, because by definition it goes 0 torque, and but from here also you can get to a situation that torque will be 0 when s is 0. Okay, when s is 0. So actually, you see that now the red line actually, if you see, the red line is nothing but load torque line. It can be of any shape. Okay, so the load can have different natures. So you can have a constant torque load, like where the torque will remain constant at all speed. You can have a load corresponding to proportional to speed. You can have a load proportional to square of the speed. You can have a load proportional to cube of the speed. Okay. Any other arbitrary characteristics also you can have, right? So I have shown you a simple characteristics where there is a nonlinear characteristics between the load torque and the speed, right? So now initial operating point, it was shown at this point. So at the point where the red curve is the black curve. Okay, that was the stable, that was the initial operating point. Now why I say initial operating point? Because it is the point where the motor torque equals the load torque. So now it is a balance, because load torque acts against the speed, and motor torque tries to drive the load torque, right? When these two becomes equal, so you get a situation where you have a operating point. Now whether it is stable or unstable, so you have to see from the derivative, right? Or you have to see when you perturb it from this position, so you see how it happens. So in the motor dynamics, I think this portion has been will be covered by the other part, covered in the other part. So you see that this is stable. I just as I have uttered the uttered the word, so I will explain it is stable here. So if you see, if you perturb it, if you go beyond the load torque, right? If you go beyond the load torque, so you get a situation where the load torque is more than the motor torque. Okay, if you shift from this operating point, indicated that S equal to Sm, or it is written that operating point Tm equal to TL. So if you go to right side, that means it goes above. If the speed goes above, right? If the speed goes above the speed, so load torque will become larger than the motor torque. So I mean the dynamic equation, if you see the motor is actually Tm motor torque equal to TL plus J d omega dt plus B omega. I think you have learned that. So now from here you will see that the speed will deaccelerate because the TL is more than Tm, so d omega dt becomes negative, so motor will deaccelerate. That means the speed will fall and come back to this. Now if you go to the left side, that means if it is not operating there, so if it is going in the left side, so at this point you see that motor torque is more than the load torque, so d omega dt is positive, so then motor will try to accelerate. So that means this becomes the stable operating point. So you have to see the slope of the load torque and the motor torque curve to judge the stability. So that is a separate issue. So now supposing it is operating at this operating point, so I want to shift the operating point to a new one, so which has been shown in little bit bluish circle. So where I said that if the load must be operated here, what if the load must be operated here? That means if we want to shift the operating point, right? If I at a different operating point, that means I don't want this much of torque, so I want lower to operate low torque. So then these characteristics will not hold good. So motor will always try to go to the initial operating point. So you have to do something with the characteristics. Okay. So now there comes that there comes your speed control mechanism, right? There comes your speed control mechanism. So you have to modify your motor characteristics so that your new stable operating point becomes the other point, right? That is why we require drive system, right? Because you want to operate the motor at different load operating points, because load can have different demands. So that's what. Now you see again our torque equation, what we shown earlier. So this torque equation has these variables, like one is Vs, right? One is Vs. Another is actually, if you replace omega s with 4 by p pi f, right? So and frequency, and another is number of poles. So why this torque relation is there? If you see the previous slide that I showed, so when you try to vary the speed, you vary the torque also. That means you have to see both. Means how you can vary both torque and speed to shift the motor characteristic to match the new load operating point. Is that clear to you? Is that clear to you? বোঝা গেছে?
Yes, sir.
হ্যাঁ স্যার বোঝা গেছে।
Okay, so now as we have three variables, so we can vary the speed with the help of all the three quantities. So one is, that's what I was mentioning earlier, varying the stator voltage because the torque is proportional to Vs square, and also by varying the frequency because it is inversely proportional to frequency, what I have said, and again it is proportional to poles. Okay, so we can vary the poles. Now you will see how pole changing. Now this one actually I could not draw, so I had drawn on paper and then taken photographs. So is it visible to you? Because on board I have shown, but here it is in this mode.
স্লাইডটা চেঞ্জ হয়নি এখনো।
আচ্ছা স্লাইডটা wait for some time. I'm
হ্যাঁ
also
স্যার
I'm
এবার
also
হয়েছে।
okay. So because the slides I have taken photograph are having a larger MB megabyte, so larger memory, so it takes time. Maybe it is taking time. So okay, is it visible now? Huh?
Yes sir.
Okay. So now the question is, how do we change the poles? Okay. So now you see that I have shown a diagram having say 8 poles, like say these are the winding diagrams. Now I have this kind of winding. One is like this, and it is connected like this in this series. Okay. So now you see another two. Now this CD, these two CD, AB is C through this. I'm showing the arrow. You can trace also. So first and third is for AB, right? Second and fourth is for CD. So now you see in the top actually it is shown that how the current is flowing. I mean, if it is coming out, so it is dot. If it is going in, it is cross. So dot cross like that. This is the winding diagram. So now the formation of poles, you see, if I am assuming that clockwise is going in, that means north pole, and anti-clockwise is for south pole. So NS, 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 and NS. Okay. So ultimately, it will form 8 poles, right? So now, if I connect them, all these coils in series, so A, B, and then C, D, right? Or I connect them in parallel, so A, B, and C, D. So both will form 8 poles, right? And then when series went parallel, you know that parallel for increasing current. Now series is for actually increasing the voltage rating. So which coil can withstand this much of voltage? So if I have more voltage, so I will connect more in series. So in this actually the coils are designed. Okay. So now if I reconnect them, if I reconnect them in a different manner, like that, so my AB is not connected to CD, B is not connected to C, so B is connected to D, right? So if I connect A and then B and then D and then C, so the thing is reversed. Okay, so we get N, S, N, and S, right? So we get only 4 poles. So in between we don't get any we don't get any poles, right? So we get only 4 poles. So in this way we can actually vary the number of poles in the winding, right? We can connect 8 pole machine into 4 pole, like that way actually, into 2 pole also we can do. So then you see the characteristics will be shifting like this. Say for 8 pole we have a lower synchronous speed, for 4 pole we have a larger synchronous speed, and for 2 pole again we have a further larger synchronous speed. And if we have a load torque like this, similar load torque, so the operating points will be automatically shifted from A to B or B to A, depending on that you are changing. Either you are changing from 4 to 8 or 8 to 4, like that, right? So then actually this pole changing technique was followed earlier in early 90s, early 90s, no, early 1900, in the 20th century. So because those time we did not have that much of advancement in semiconductor technology to develop the modern control schemes with the help of semiconductor switches and then microprocessors and etc. So just physically we have relays or contactors that can shift that can shift the winding connection from one to another, and then pole shifting was there. Okay, so the thing is that this thing became obsolete because it has got 2-3 drawbacks, mainly 2 drawbacks. So first drawback is, say we have a 50 hertz supply. Now you connect it in 2 pole, so you get a speed which is near 3000 rpm, because 50 hertz 2 poles in, we have a rpm value around near 3000, right? So if you reconnect this as 4 pole, so it will be at 1500, near 1500. So if you neglect the slip portion, okay. And then again 8 pole and again 6 pole will be 1000, right? And 8 pole it will be 750, like that. So therefore, if you a speed which is in between, like say I want a speed of near 2000 rpm, so I cannot achieve this with the help of this pole changing technique with constant frequency supply, right? So this was not a very effective one, but still nothing is there, so this was okay. Then after that, this type of speed control was not really applicable to the slip ring induction machines, because you see that to have a successful torque, steady torque production, the stator number of poles has to equal the rotor number of poles. Okay, otherwise there will be difference of synchronous speeds, and then there will be an average torque which is zero. Okay, over a complete cycle. So there, the stator and rotor poles has to be same of same number. But you see that the cage machines, the rotor actually is of cage type, and there are bars and end rings, and the rotor conductors carry current in such a fashion that they assume same number of poles as the stator winding. So we did not have to bother about. But when it comes to slip ring machine is a wound rotor actually. Rotor is wound with a similar winding corresponding to the stator winding with same number of poles. And now, whenever a pole changing has to take place in the stator side, and the rotor pole also has to be changed in the same way. So then the rotor external connection is only through the slip rings. So now you see, if the rotor has 8 coils, right? Naturally, 16 number of slip rings has to be brought out from the rotor shaft extension. The space and then the complexity and all made it not very popular one actually. It's only of academic interest that it can be done. So these two methods have made scheme almost obsolete, and nowadays of course you have much modern many modern schemes which is available. So this is not followed business, but okay, this is for an academic interest. This is one of the techniques that can be employed to vary the induction motor speed. Okay. So then comes the second, variable voltage. So now variable voltage, I think this variable voltage is 1122. So I should leave now actually. Huh? So I have to start for my university. So I think up to this I stop here. So next day I will be starting from here. Huh? Variable voltage and constant frequency. So so one thing that you should send me your roll sheet along with that presence, today's attendance, whoever is there. Acha, if you have sent, no problem. So any queries you have over this lecture or from this explanation what I have given, you can take 2-3 minutes, and if you have anything, any point, if you missed or if you could not follow. Is it all right?
Yes, sir.
So okay. So we stop here today. Huh?
Thank you, sir.
Okay, sir. Thank you, sir.
Okay.